we're going to talk about a method for solving pretty general equations. So we're going to look at equations of this form f of x equals 0, where here I've written everything as a vector. So for instance, I might have something like f of x1, x2. I might have a function of 2 arguments equals 0, and this would be f1, and then f2 of x1, x2 equals 0. So I'd like to think about this as a system and solve it. And you might say, well, what if I have something on the right-hand side other than 0? Like maybe I would have, g1, x1, x2, for instance, and g2, x1, x2. For instance, maybe I want to solve 2 different equations. Well, then I can just subtract over to one side and deal with this as a case of the as a special case of this original equation, or a version of that equation. So by subtracting over to the other side, so long as I have some ability to do that, we can put this in a framework of just finding when the right hand side is equal to 0. So another thing you might say is, well, what about if I have more equations than unknowns, or more unknowns than equations? And generally, if we think about analogies with linear algebra, either you'll have a system which is overdetermined or underdetermined, and that's kind of a special setting. So we won't consider that case right now. Also, this isn't limited to just 1 dimension or 2 dimensions. We could have thousands of variables if we wanted to. The departure from linear algebra is that there's no assumption here that these functions are linear whatsoever. So let me give maybe a more concrete example. Let's consider something like this. X squared plus y squared equals 4. So we have a circle, and then we'll have y equals x squared minus 1. So for something like this, we can of course view this geometrically. So the first equation gives us a circle of radius 2, and the next equation gives us a parabola, something like this. And we have 2 intersection points here. So the solution of this system is a set of 2 points, which we could solve pretty easily, but I'll leave it up to you if you want to try solving that algebraically. All right, so the idea is, how could we do this if we have something significantly more complicated? For instance, if I change this maybe to cosine of y and equals, say, plus tangent of xy, all of a sudden we're in a realm where this is looking like a pretty difficult problem. All right, so in this case, so we'll use this one as just an example, but let's translate this a little bit into that language we were looking at a minute ago. So here my f1 of x1, x2 would be, so I'll think about x as x1 and y as x2. So then we just subtract everything over to one side. So I'd have x1 squared plus x2 squared plus x2 squared minus 4. And then for the second function, we would have f of x1, x2 would be, let's see, and then we could have, well, I'll put x2 here, that's our y, then we subtract it off x2, and I'll arrange them this way. It's not too important to necessarily arrange them in a certain way, but I'm just kind of doing that for consistency later on. So we'll see when we code this thing. It'll be nice to have it sort of labeled in this way. Oops, and I've written this one. This should be an x2, and this should be an x1. There we go. All right, so that's the general type of problem that we want to attack. And Newton had a really interesting approach to this type of equation. I believe he was only considering the one-dimensional case. And the one-dimensional case is pretty nice because there's a great picture that goes along with this that you might have seen in a calculus course. But let's remember it anyway. So I have some function like this, and let's start off with a function that actually has a 0. Otherwise, it's going to be hard to find a 0 if there's no 0. So we have something like this, f of x. And I have some maybe initial guess. So this point might be pretty hard to find. For instance, if this is a fifth degree polynomial, we know by Galois theory that we could have a really challenging time, and we might not necessarily have a solution by radicals for such an equation. So I start off with something like this, and then I have some initial guess, x. Well, this is probably not the right guess. We could just plug it into f and see if it's 0, and if it's not, well, we maybe have to give up. But let's say I have some type of guess here. Let's say xn, maybe I'm at the nth guess. And I can evaluate the function right there, and I can think about the tangent line that sits on this point. And the idea is that hopefully this tangent line hits at a 0 that's a bit closer than, hits at a point which is a bit closer to our chosen 0 than before. Now, that's not always going to happen, right? We can have situations, for instance, we might have a very unlucky guess if we have something like, let's say we're looking at a cosine graph, something like this. Cosine at 0, its tangent line will be just completely horizontal. So if we're unlucky enough to guess 0 as our initial guess, we go up to the line, we go up to the function, we draw our tangent line, and we never hit the axis. We just go off in either direction with no luck. So we could get an unlucky guess in that way. There are other situations that can happen. You might have multiple zeros, like we had in the previous picture. I might be trying to solve something like this, where I have several different zeros here, and then I'd want to choose an initial guess which is close enough to the 0 that I'm looking for. Or if I don't have a good guess for that, I'm not really guaranteed that I'll necessarily drift to one or the other. And you have situations which are always a little bit hard for me to draw, but there are situations where you might say pick a guess that leads to something larger, and then that's not going to be quite right. You pick a guess here, yeah, there we go, that leads down to the axis that, well, that one's going to spiral in. I have a hard time drawing these, but you do have situations where you can sort of spiral out, getting farther and farther out. So this method does not always converge. However, it's a very, very popular method, and the reason is because when it converges insanely fast, and we'll prove that. So this is the general setup, and we can figure it out pretty easily how this should work. First of all, we need to write down an equation for the line. Let's call the line L of x. In fact, I'm going to jump straight to the multidimensional case because it's just the same as the as the one-dimensional case. So we have a function f of x, and we're sitting at a particular guess f of xn, and I can write down, say, the linear approximation to this line. Well, we know what this point is. This is just f of xn, right? And then we know what the slope is. So L here will be a vector in general. X will be a vector. F will be a vector. Everything here is a vector. And then we plug in, we would look at the derivative. I'll write it in one-dimensional form first, f prime of x, then times x minus xn. And you might recognize this as just the usual Taylor series expansion. So you would have higher order terms if you were having a higher order Taylor expansion, but here we're just doing a linear approximation. So in higher dimensions, instead of f prime, we would write gradient of f. So the gradient of f evaluated at xn, maybe I'll put many parentheses if you want to look at it like that. And here, again, everything is a vector. So just to be clear, the gradient, so this is where the gradient of f, the gradient of a vector, is a matrix. It's the Jacobian matrix. So it's the matrix dfi, partial derivative fi with respect to the jth component. So I and j go from 1 up to n, where we're thinking of a map. F is a map from Rn to Rn. So we have this linear approximation, and then we can actually just solve this fairly straightforwardly. So remember that the whole idea behind Newton's method is to go down to the axis to find that 0. So in order to do that, we'll just set 0 equal to L of x. And remember, L of x is f of xn plus gradient f xn x minus xn. All right. Now it's just a matter of rearranging a little bit and seeing what we get. So first thing we'll do is we'll subtract this guy to the other side. Now this piece is a matrix, and one of the assumptions behind Newton's method is that this gradient is not equal to 0, and that actually has a physical meaning. Or to say this gradient is this matrix, this Jacobian matrix is invertible. If the Jacobian matrix is not invertible, that corresponds to, if you think about the one-dimensional case, that corresponds to some kind of flat point. And we saw if you choose that, you never hit the axis, right? There's no solution to that equation. So we'll assume that this guy is invertible. In fact, we'll assume a little bit more about this, but I'll talk about that soon. And so we have minus f of xn equals the gradient of f of xn times x minus xn. And this allows us to solve. We can just invert this. So this implies that negative gradient of f at xn inverse, it's equal to x minus xn. All right. In fact, we don't need the parentheses any longer because now we can just solve for x. So this means that x is equal to xn, that's this xn I've added to the other side, minus gradient of f of xn. We're just rearranging here a little bit. Something like this. And so the idea is that this is our new guess. This is Newton's method, is that, okay, I got a little bit closer from this iteration. I guess I'll go back to the, I'll go to this picture. We've gotten a little bit closer. So this would now be our xn plus 1. So we're sort of moving a little bit closer to the 0, we hope. And so we get Newton's method. We have xn plus 1 is equal to our old guess minus, oh, I forgot to write this. I forgot to write it in a few places. F of xn, f of xn. And just to kind of keep everything clear in our minds, this piece is a vector. And so we're applying an inverse matrix to that vector, getting out a vector and subtracting that from a vector. So when we're all done, we have a vector. Okay, so it's minus this gradient, fxn, inverse applied to f of xn. Right, and so this is Newton's method. Great. Okay, so let's see how to prove that this converges, and more importantly, maybe under what assumptions it converges. So we'll have some standard assumptions on the function f. On this f. So we'll assume, so they're standard for Newton's method. First of all, we'll assume that there's a unique solution. Now this can certainly be modified, but for the purposes of the proof and to kind of keep things a little bit simple, we'll assume that f of x equals 0 has a unique solution. X star. Maybe I should say where this f is mapping. So in fact, we don't necessarily need to assume that the underlying domain is all of R. N, we can assume that f maps from some domain omega. Now, there are situations in which sometimes you can go outside of the domain. I'll mostly ignore those cases for the time being, but the algorithm itself isn't necessarily restricted to cases where you have the full space. So you have some type of, we'll assume that you have a unique solution in omega. All right. Second assumption, and this one's a little bit technical, but we'll see where it comes up. And that's that this gradient of f, the matrix gradient of f, write that a little better, the gradient of f, which maps from omega into r n cross n, right? So I take a point in the domain and I get a matrix out. So the target gives me something in r n by n is Lipschitz continuous. And so Lipschitz continuous is a little bit of a stronger condition than continuous. And it just means the following. So i.e., Lipschitz continuity means that if I take, in this case, it's just some, say, matrix norm. If I take gradient of f evaluated at one point minus gradient of f evaluated at another point, that's bounded above by x minus y times some constant gamma, which is sometimes called the Lipschitz constant. And this is for all x and y in omega. So I should say there exists some real number gamma. We normally want something bigger than 0, otherwise f is just, or gradient of f is just constant. We have something like this. And then our last assumption is that f is, sorry, the gradient of f at x star is non-singular. So that, right, i.e. gradient of f at x star inverse exists. All right. So this is kind of a standard setting, right? And so if notice this, if you had something like this, this rules out cases where you just kind of come down and touch at a single point, which sometimes can cause a little bit of trouble for Newton's method. Okay, so theorem. So let the standard assumptions above hold. Then you get a number k, some k bigger than 0, and some delta bigger than 0, possibly small, such that if your initial guess x0 is in a ball centered at x star of radius delta, then the sequence xn, so this is the sequence of guesses generated by Newton's method so it converges to x star, but more than that, and it satisfies. So this is what really makes Newton's method powerful. And all these, hundreds of years later, we're still using it. X minus x star is less than or equal to k times xn minus x star squared. So that square is very, very powerful. And we'll see this in a little bit. What does that actually mean in terms of computational speed, right? But one way you can think about this is, if my error at some stage, so let's assume that the k is not too big, say maybe k is equal to 1 just for thinking about it. If my error at some stage is, say, 1/2, then one step later, My error is a quarter. A step after that, my error is not just an eighth, right? It would be a quarter squared. So my error is now 1/16, or and so on. You get this very, very fast accumulation of, or very, very fast decrease in the error. Or if you want to think about it in terms of decimal places, right? If I have an error, if my accuracy is 1 decimal place, so my error is a tenth, one step later, my error is 2 decimal places. But then the next step, my error is I'm accurate out to 4 decimal places. One more step, I'm accurate out to 8 decimal places, and then 16 decimal places, which in a computer, we know that 16 decimal places with floating point accuracy is usually about the best we can get. I mean, it's crazy fast convergence when it converges. And that's all kind of tied up in this little assume that x0 is close enough to the exact to the solution you're trying to get, and that can be pretty hard to do sometimes. A lot of times there's sort of a natural or initial guess that's kind of shouting out at you. For instance, if you're solving ordinary differential equation, and at every step you're doing a Newton iteration, well, probably you want to use, the value of the solution that you had at the previous time for your next step in the Newton iteration. So sometimes it's kind of, maybe there's like a clear answer of how you should choose the initial guess. But anyway, so let's take a look at this proof, which I think is a pretty nice proof. It illustrates several different methods, some of which we've seen before, and some of which well, they're just sort of nice to think about. So we'll use this kind of a representation. So first of all, notice that, okay, proof. So I could just say we'll use this representation, but I thought I would just write it down for you a little bit. So if I have f of xn, I can rewrite this as f of x star minus an integral from 0 to 1 of f prime. And by f prime, I mean the gradient of f at xn plus t times x star minus xn. Let's write it down and then talk about it. That whole, this whole guy is a matrix, right? Evaluated at a particular point, times x star minus xn minus xn dt. Now you might say, well, okay, where does this kind of thing come from? But it's really just coming from the fundamental theorem of calculus. Notice that if we take this whole, so let's check that this is true. So if we rewrite this as integral from 0 to 1 of just gradient of f, and then I write this as xn plus t times x star minus xn. So that's t times this thing. D, so I want to pull this thing inside, d xn plus t times x star minus xn. We see that this is really just coming from substitution, right? So for instance, you could relabel this thing as u, and then you would have du here, thinking about these things as vectors. And then this piece would just be, by fundamental theorem of calculus, right? It's just the integral of a derivative at the end of the day. If it helps, you might want to write this out in the one-dimensional case and just write this with an f prime. Remember that this is a matrix times vector, right? So this is a matrix vector product, which yields a vector. So this is just f of xn plus t, plus t times x star minus xn, evaluated from t equals 0 up to t equals 1, which is just f of x star right? If you plug in t equals 1, then the xn cancels, so you get f of x star minus, and then if I plug in t equals 0, you get f of xn. And then after just moving this to the other side, that's what we have up here. All right. So we have a way of, I mean, you might also say, why have we done it this way? Why are we looking at this particular thing? Well, here we have a gradient, which shows up in Newton's method, gradient of f. And then here we have evaluation of the function at our guess and at the exact point. All right. Well, from this, from this, let's introduce, so to note En to be our error. So in this case, we'll write it as xn minus x star. Sometimes we write that as maybe the exact solution minus xn, minus the iteration in other applications. And it's just kind of whatever's most suitable for the stage you're at. So then we can write Newton's method. So we can subtract x star from Newton's method to obtain, and we just have E at n plus 1 is equal to En minus gradient of f xm. So maybe I'll write it down this way. So we had xn plus 1 is equal to xn minus gradient of f xn inverse times times f at x n. Oops, subscript. I think I was mostly using subscripts on this. So we can subtract x star from both of these, and then notice that that's just the error at the end stage. For some reason I started writing subscripts instead of superscripts. So I guess I'll write this as a subscript as well. Okay, there we go. En. So we can go a little bit further than this. So from here, we can rewrite this En plus 1 as I would like to factor out this matrix, but how can I factor out a matrix like that? Well, I'll need to multiply by the matrix. So I have an inverse here, f of xn times En, then minus f at xn, like that. So, right, if I multiply this back, then the inverse matrix times the matrix itself will just give me the identity, giving back this En. And then the rest has just been factored out. So if we think about, so since f of x star is equal to 0, right? Then going back to, sorry, I'm at lowercase. I have a capital F in my notes, and for some reason I switched to lowercase. So since this f of x star is equal to 0, we actually, at this stage, we have a nice formula for f of x n star, excuse me, for f of x n in terms of this integral. So it should be, well, it would be minus. I'll write it here as minus, let's zoom out a little, gradient of f xn plus t x star minus xn times x star minus xn dt. But this x star minus xn, this is negative En. And so we can write this a little bit differently. So this is just the positive integral 0 to 1 of the gradient of f times xn minus t. And then we notice that this thing itself is another, well, so this guy is negative En. So I can write this as just a minus, so this plus becoming a minus, En times En dt. All right. So substituting this into this expression for f of xn, we can have the following estimate. So we get en plus 1 is equal to the gradient of f of xn inverse. That's just this piece. But then times the gradient of f of xn en minus the integral 0 to 1 of gradient of f xn minus ten times en dt. And finish off with big parentheses. All right. So we can write this a little bit further as just gradient of f xn inverse times the integral from 0. So if I sorry, just one moment here. Yeah, times the inverse. I'm just going to factor this en out. Notice that en doesn't depend on time, so I'm allowed to just factor it out of this integral and then out of everything. So this thing becomes excuse me, it's an xn inverse times integral 0 to 1 of gradient of f of xn minus gradient of f xn minus ten dt. All of that applied to en. You might say, what happens with this? Well, there's no dependence on t for this, and I'm integrating from 0 to 1. This is since, say this thing is independent of t. So we can just push it inside of the integral and just integrate the function 1 from 0 to 1 and get back 1. Sorry, that parenthesis should be here. Okay. From here, we're in pretty good shape because we can now just take a norm of en plus 1 and see that this is bounded above by the matrix norm of the inverse of the Jacobian at that nth point times the integral from 0 to 1 of, and then one of the properties of matrix norms, in this case, it's really just kind of acting like a vector norm, but we can push these inside of integrals just in the same way that you can for, say, absolute values. So we have something like this, xn minus ten dt times the norm, the vector norm in this case of en. So it's a little bit funny looking, but not too bad. We now have an en plus 1 bounded above in terms of the previous error, and we just have to deal with the rest. Now, this part might look pretty wonky, but don't forget we have the Lipschitz property. So this is bounded above by the Lipschitz property. So here we have gradient f xn inverse norm. And then the Lipschitz property says that this is just bounded above by, well, we can leave the integral here for a minute, but we'll see we don't need it, times gamma times the difference between these 2 points. But the difference between these 2 points is just t. So it's a negative t if you like, but it doesn't matter because we're in a norm. So ten dt times sorry, that should be a subscript, times en. And then that t can come right out of the norm. Notice we're integrating from 0 to 1, which is a positive interval. So t is positive. So when I pull it out, it doesn't need an absolute value. And so there we get gradient f xn inverse times gamma times the integral from 0 to 1 of just t dt, and then times en, and here's that square. And of course, this is just equal to 1/2, right? 1/2 t squared, plug in 1 and 0, or see it as a triangle, area under a triangle, if you want to compute that one geometrically. And so you get, so let's sum up. So this means that the error at the next step is bounded above by the error, by the this particular gradient times is a gradient of f evaluated xn inverse times gamma over 2, and all of that times e n squared. All right. So now the issue is that this piece, oh, sorry, that should be a norm there. Oh, we have a norm. Here we go. The issue is that this piece we would like to somehow bound above, and it doesn't seem very good because n could be changing at each step. So we would like to bound this above by something constant, but we haven't used the fact that we're close to the exact solution yet, right? So since xn is close enough to x star, and that's a delta coming up in the proof. It's close enough to the x star, and since gradient of f at x star is non-singular, then there exists a small ball at x star, some delta bigger than 0, some small ball, such that if xn is in that ball, that's an element of symbol, then we have en plus 1. Sorry. Then we have that this gradient f of xn inverse is at most 2 times the gradient of f x star. It's supposed to be a gradient. F x star inverse. And this is a property of it's just coming from the idea that these functions are, have a little bit of continuity. So this is kind of just a nice property of matrices, that if this thing is non-singular, I can get close enough to it. So what does that mean? That means that we can use this for an upper bound. So this implies that en plus 1 is bounded above by gamma times, well, we had 1/2 gamma, but now it's times 2 gradient fx star inverse. Sorry, that should be a times 2 times this norm times en squared. And this, so the 2's can cancel if you want, but this is our k. And that's it. So if you want, well, I guess we should do a little bit more. So we proved the inequality. If you want to see it if you want to see that it actually converges, right? How does this actually show convergence? So this was kind of the main piece, but now you can let x0 be in, say x sub 0, be in this ball at x star delta. Again, how do you actually get close enough? What is close enough? Well, you might be able to evaluate this expression and get some kind of idea, but in order to do that, you would actually have to already know what the x star is. So if you have a pretty good guess of the x star, it can work, but this theorem doesn't give us like an explicit way to choose our initial guess. Anyway, so if you're within this ball, then, right, you have, for instance, E1 is less than or equal to k times E0 squared, but that's then less than or equal to E0 times delta times E0, right? And then that's less than, say, if, let's say we might need to and choose delta possibly smaller. Forgot to mention this. So that k times delta is less than 1. So then this is less than E0, and that's less than delta. And so then by iterating, or induction, if you like, one can show that these guys are in increasingly smaller delta balls, right? So if you think about E2 here, you're going to get less than something within delta squared, and so on. So, and let's do a little bit more. Delta itself has to be less than 1. Then that En, keep writing superscripts, I'm sorry, that En goes to 0. Sorry, that should be a 0, 0, 0. This is an E1. Okay. So that's that shows the proof. And I think I'm going to stop here. And if we have more time, I'll show some coding for this. So thanks.